All right, so let's get going with chapter 2. We're going to talk about atoms, molecules, and ions. Okay, just a little history for chemistry. Chemistry has been around, maybe not as identified as chemistry, but chemistry has been an investigative tool by people for millennia, back to the invention of fire. It started going in earnest with the alchemists in the years between the Roman Empire and the Renaissance. So we started getting alchemy in there, and then the modern chemists kind of grew out of that. And by the time modern chemistry started to take shape, several elements were already known, elements that you'll find on the periodic table. So they had been identified for us by that time, and several mineral acids had been prepared also. They were extensively used in trying to transform lead into gold, for instance, or find the elixir of life. Many of them thought that mercury was the elixir of life. We won't go into that. And what I mean by mineral acids are things like hydrochloric acid, muriatic acid that you etch your concrete with before you seal it, right? Sulfuric acid, and these are all aqueous preparations. Nitric acid, those are what we call mineral acids. There are several others. Those are just examples. Robert Boyle is by and large considered to be the first chemist, in large part due to his publication in 1661 of The Skeptical Chemist. He was what we would call a quantitative investigator. In other words, he made measurements that gave him numbers. And he performed experiments that were designed beforehand to answer a question, rather than just going into the kitchen and throwing stuff together and see what you get. Sadly enough, there are some scientists these days who still do that. He developed the first definition by experiment of the element. And the element is the simplest form of a substance that can be obtained by chemical degradation. That is, you break it apart chemically, and once you get to a certain point, you can't break it any further. And that's identified as an element. And all substances that we know are composed of combinations of those elements. Now, the symbols that we use in the periodic table, these were, and my mind's gone blank again. I'll remember his name in a minute. It gave us this system. These are possible symbols that could have been adopted for the elements. And I'm glad they didn't, because this is a mess. There's no rhyme or reason to it that I can see. But these are elements that were used up until modern chemistry settled on this format with just the letters. Okay. So there's a difference when we talk about the sciences. We mentioned earlier, I think in chapter 1, the difference between a law and a theory. Right? Laws generally come first. You develop the law because maybe you don't have the technology or the expertise that allows you to investigate a phenomenon to the extent that you can propose a why. All you can say is what. So the laws say what happens. And these are some of the main ones that developed during the birth of modern chemistry. And one was proposed by Antoine Lavoisier, who was a Frenchman, obviously. He had the misfortune of being active around the time of the French Revolution. before the revolution came, he was wealthy. Most natural philosophers, they called them, we call them scientists today, were active as independently wealthy persons. They didn't get funding from someplace else. Usually they had the money to indulge in these extra activities. And Lavoisier and his wife was very instrumental in helping him with his experiments, proposed this law of the conservation of mass. And all he said was that during a chemical reaction, the mass of the reactants is equal to the mass of the products. And he performed experiments to show it. And some of the experiments he tried to do came up with different masses for his products, usually less than the reactants. So he spent time trying to figure out where those products went, and he found them. And eventually he was able to propose law of conservation of mass. So if your mass is radically different for the products from the reactants, then you know you're missing something. And that just says that whatever they're made of, these substances, the products or the reactants, they're indestructible. In other words, you can't get something for nothing. Then I think Proust, Robert Proust, I can't remember his first name. It looks like a French name, but he was really English. And that's not surprising, right? Ever since the Battle of Hastings, you've had the French kind of insinuated into the English language by the Normans. The law of definite proportions. Definite proportions. All Proust was saying was that when you had identified a compound, that it didn't matter the source, where it came from. Was it the product of a reaction, or did you purify it from a natural source? Like water, for instance, right? We can distill water and it can be reasonably pure. And then you can determine how much hydrogen by mass and how much oxygen by mass are in ratio to one another. Okay, that's the composition of the compound, right? We know now that water is that, 2 hydrogen atoms and 1 oxygen atom. And Proust didn't know that at the time. Nobody did. They worked with masses only. They didn't work with individual atoms. That hadn't come yet. Well, if you purify water from a natural source, you get a pure compound, a pure substance, right? If you react hydrogen and oxygen, you also get water. Like in the space shuttle engines and some rockets now, they still use liquid hydrogen and liquid oxygen, combine them and whoops, there you go. Or if you have an accident, like the Challenger, you blow up all of a sudden. But the end product is water. So water from 2 different sources, it doesn't matter. They have the exact same ratio of mass of hydrogen to oxygen. Okay. So this would be, say, a ratio of approximately 2 grams of hydrogen to every 16 grams of oxygen. That ratio is fixed, 8-to-1. No matter where it comes from, that's definite proportions. Okay. Then John Dalton, not too long after that, proposed another one that students sometimes get mixed up with definite proportions. It's the law of multiple proportions. And remember, we still don't know why it is at this point in history. We don't know why these ratios are the way they are. These laws are the way they are. Multiple proportions simply says, if you have a binary compound, that is 2 different elements in combination, that and you have different compounds of those same 2 elements, And I like to use nitrogen and oxygen. Right? We now know that you can do this or that. Right? Same two elements, different ratios, and they're different compounds. They have different identities, different properties. Dalton said that if you hold one of them as a base unit, like this one is 1, 1, and 1, then the other one is always in whole number ratios. 1 to 1, 1 to 2, 1 to 3. Whole number ratios. That's multiple proportions. Now, Dalton later is going to propose a theory that explains all of these, plus some others. And that's his atomic theory. It seems to be characteristic of the sciences that most scientists work in their little bailiwicks, or they propose answers to small questions, and they tend to accumulate over time. And every once in a while, you get somebody with the brain that synthesizes all that information into a coherent story. And it's usually a theory. Dalton was one of those. So he proposed his atomic theory, and the postulates of this theory explain all of those laws. Okay, the first postulate is each element is made up of tiny particles called atoms. Now, this was not an original thought from Dalton. He stole this from the ancient Greeks. The ancient Greeks, some of them, not all of them, but some of them believed that everything that we see is made up of an elementary particle called the atom. And they called it the atom. I think I told you this last time, didn't I? A means not, or maybe I'm getting you mixed up in my other class. A means not, and Greek for tomos is cut or divide. So this particle is not cut. In other words, it's the smallest particle that you can get for matter. Now, the Greeks thought that everything you see is made up of the same atom. Okay, now they're painting themselves into a corner, because now they have to explain, if everything's made of the same atom, how do you get such different substances out of that same atom? Right? They had trouble with that one. So they invented various convoluted mind games to answer that question. Some of them invented elementary forces or parts like earth, wind, fire, and water, to help explain. All right, so the Greeks were not famous experimenters. Most of them were and when they taught their youth how to do things like math, they just threw it in the dirt and you had to memorize it. Okay, the second postulate for Dalton's atomic theory was that atoms of a given element are identical, and the atoms of different elements are different atoms. So that's how Dalton solved this Greek problem. He said, they're not all made of the same atom. This element's made of that type of atom, and this element's made of a different atom. But it's still the smallest particle of that element that retains the properties of the element. Then he said that chemical compounds are made of atoms from two or more different elements. You combine them, they bond in a certain way, and they produce a different substance. That's how we get this variety of substances. As long as they're not elements, they're combinations of different elements, atoms of different elements. Okay, so that's how he explained his multiple proportions. He said the nitrogen and the oxygen atoms combine, but for the different mass ratios, there are different numbers of atoms combined to make those different substances and the multiple proportions. Okay. He said in a chemical reaction, all the atoms do is swap partners. Right? It's like a dance. where you dance for 3 minutes, somebody blows a whistle and you switch partners. It's just a rearrangement of atoms. That's the chemical reaction. So that explains Lavoisier's law. In other words, if you got the same number of atoms before and after, you're going to have the same mass. And let's see, we've already explained Proust's law of definite proportions by the arrangement of atoms. So if you have two different substances, they're going to have exactly the same number of atoms arranged per unit. Okay, now beyond that, we get to Gay-Lussac and Avogadro. They both worked on chemical reactions and trying to figure out Dalton had already proposed, or just recently proposed, this idea of the atomic theory. So scientists were taking that and trying to answer questions that they couldn't answer with just knowledge of mass. And Gay-Lussac and Avogadro didn't actually do these experiments, but he was given credit for the hypothesis because if he hadn't proposed this explanation, then there wouldn't have been any further developments. So Avogadro said that, and they were working with gases primarily, because gases were easy to handle, and the instrumentation, the technology was okay for dealing with gases. And the other very important point is, for dealing with gases in a physical realm and later in chemical reactions, well, physical for sure, one gas is as good as another. In other words, air will give you the same results with the gas laws as pure helium. So Avogadro said, with these two gases in this container, of course, it has to be a sealed container, right? Because the gas will expand to fill its container. If you open the thing, it'll just all come out until the pressure is equalized. You have these two gases here, and they're both at the same internal pressure inside. And they're the same volume. And they're at the same temperature. Then they have to have exactly the same number of particles, molecules, or atoms. Exactly the same number. And we use a little n for that abbreviation. Okay? That's basically what Avogadro was saying. Now, how does this relate to solving the mass question? Hey, go ahead and sign in and grab a copy of everything. It solves the mass question. Actually, let me see, I don't want to steal my own thunder. Oh, okay, good. Avogadro had a student. His name was Cannizzaro. They were both Italian. I can remember how to spell his name. I think there's double letters in there somewhere. But Cannizzaro took Avogadro's hypothesis and published a paper. And there was a big meeting in southern Bavaria at the college at Karlsruhe, Germany. And all these university professors and scientists from companies had gotten together with one objective: solve the problem with reactions that wouldn't behave. Because they only knew how to combine things by mass. That's all they knew. So when something went wrong, their knowledge base didn't allow them to fix the problem. That wasn't good for college professors because their publications were worthless. And it wasn't good for company scientists because their bosses were losing money. So they got together to solve this problem, And all of them but one threw up their hands. This is, we don't have an idea. There was one presentation, the paper that was written by Canizaro. In fact, I think there are two here. Anyway, he took Avogadro's hypothesis, and he gave Avogadro credit for it. That's why it's his hypothesis, not Canizaro's. And he said, if you have this arrangement like this, equal pressures, equal volumes, equal temperatures, and consequently equal numbers of particles, then the difference in masses is due to the difference in masses of the individual particles. If you've got the same number of particles in each one and they've got different masses, then say this one's heavier than that one, the individual particles here must be a greater mass, each one. Okay, that was the groundbreaking revelation that they were looking for. So he handed out reprints of his paper, and they all politely accepted them, went back to their towns and universities. And some of them started reading them, and the light bulbs go on all over Europe. Finally had a way to track their reactions. They knew that masses, the mass ratios, were not the explanation for the reactions. It was the number of particles, the number of molecules, the number of atoms that were going together to make the reactions work. Now they can solve problems. That's the short version, believe it or not. Okay. Gay-Lussac also noticed, along with Avogadro, that if you had two volumes, and these are at the same pressure and same temperature, two volumes of hydrogen and one volume of oxygen, you get two volumes of water vapor. So that didn't make any sense. That, you know, math is 2 + 1 is 3. But in chemistry, 2 + 1 can be 2. Occasionally you can get 1 + 1 = 2. But it doesn't have anything to do with math. It has to do with individual particles and how they recombine with each other. So the explanation for the 2 + 1 = 2 is 2 hydrogen molecules and 1 oxygen molecule gives you 2 molecules of water vapor. That's why water vapor and hydrogen have the same volume, because they have exactly the same number of particles in them. But they will have different masses. This one on the hydrogen, if you just got 2 hydrogens in there, you're going to have four units, whatever, of mass. And if you use the same units on the other side, you're going to get, let's see, 1, 2, 3, 4, 36 units of mass. So the water vapor is going to be much, much heavier than the hydrogen, even though they occupy the same volume. All right. So now that Dalton has proposed his atomic theory, and we've gone to that far, at that time, when Dalton proposed the atomic theory, science in general believed that the atom was indivisible. It was just like a little bag of something. Then scientists in the latter part of the 19th century started investigating what atoms are made of. And J.J. Thomson was one of the first ones to identify and propose the existence of negatively charged particles coming from the atom. And he called them electrons. He conducted experiments, and all he was able to determine was the ratio of the charge to the mass of the electron. He didn't have the technology at that time or the expertise to determine what the absolute mass of the electron was. That comes later. But he did prove that it was a negatively charged particle coming from inside the atom. At that time, electricity was all the rage. You know, parties, in fact, for the past 100 years or so, one of the things they liked to do at parties was they had electrostatic generators. They crank it up, build up this charge on a glass bulb. And somebody would be holding on to a conductor on the glass bulb. And then everybody else would hold hands in a line, and they'd make the connection between this person and the line of persons right here. And once they touched, everybody would jump, and they'd all have a big laugh and go drink some more wine. But the cathode ray tube was a device that was partially evacuated, glass tube, and you had a direct current that at this time had been proven and identified as one electrode was negative and the other electrode was positive, and particles were passing from the negative electrode to the positive electrode, and they could characterize what it was doing, those particles. They knew that they had mass because they could put a little windmill inside there, and if it struck that windmill, it'd make it spin. So they knew they had mass.
Cathode rays are produced in a discharge tube. A vacuum pump is used to evacuate the discharge tube. The cathode of the tube is connected to the negative terminal of the battery, and the anode of the tube is connected to the positive terminal of the battery. It was observed that, at normal pressure, the gas did not allow the current to pass through it. However, when the pressure of the tube was reduced to 0.001 mm Hg, and a high potential difference between 10 kV and 20 kV was applied, at the end of the tube, a glow was seen on the walls of glass tube. The rays emitted by the cathode travel towards anode. The attraction of rays towards anode reveals that the rays carry negative charge. Properties of cathode rays are: 1. When any object is placed in the path of the cathode rays, these rays cast shadows. This shows that cathode rays travel in straight line. 2. When a wheel was placed in the path of cathode rays, the wheel rotates. This shows that rays consist of some particle and some kinetic energy. 3. In the presence of an electric field, the rays are deflected towards the positive plate. This confirms that cathode rays consist of negatively charged particles. 4. In the presence of a magnetic field, the rays are deflected. This shows that the cathode rays are affected by the magnetic field.
That's just an animation, and of course, probably recognize the voice was generated from the text, so pronunciation wasn't perfect. Also, the cathode ray bent toward the positive electrode is true, but the cathode ray, a negative particle traveling through a magnetic field, will bend right angles to the magnetic field. It won't bend to it. Okay. That's just a minor detail, actually. Okay. So, J.J. Thomson was an Englishman. Robert Millikan was an American. And at the beginning of the 20th century, he had the information was published and distributed. The ratio between charge and mass was given by J.J. Thomson, so everybody knew that. Millikan devised an experiment that allowed him to determine the mass of individual electrons. It's called his oil drop experiment, and I've got a video to follow, so I'm not going to bore you with details, except to say that he received a Nobel Prize in physics. Actually, it wasn't for this experiment. It was for other experiments that he did that confirmed Einstein's photoelectric effect equations. So Einstein got a Nobel Prize for his explanation of the photoelectric effect. In short, it's like photovoltaic cells. Light strikes the surface, kicks off an electron, and that produces a current. Right? So Einstein mathematically proved what was happening there. So he got a Nobel for that. And then Millikan came along and experimentally proved that his equation was correct. Okay, so Millikan in this video that's going to come up is going to show the oil drop experiment and how it works, how he determined the mass of an individual electron.
In a series of experiments carried out between 1908 and 1917, R.A. Millikan succeeded in measuring the charge of the electron with great precision. In his experiment, a fine mist of oil was sprayed into the upper chamber with an atomizer. Some of the tiny oil droplets fell through the hole in the upper floor, and Millikan was able to determine the mass of an oil drop from its terminal velocity. Next, Millikan used an X-ray source to ionize gas molecules in the chamber. Electrons from this ionization process adhered to the oil droplets. The oil droplets now carry a negative charge. The negatively charged oil droplets can be halted by adjusting the voltage across the two plates. As the voltage across the plates is increased, the velocity of the oil drops slows. As the voltage is increased further, some drops will begin to move upward toward the positive plate. If the voltage is set just right, an oil drop can be suspended. When an oil drop is suspended, its weight, mass times acceleration due to gravity, is exactly counterbalanced by the electric force applied. The electric force applied equals the applied electric field, E, times the charge on the drop, Q. Since the mass of the oil drop, the acceleration due to gravity, and the applied electric field are known, Millikan could solve for Q, which is the charge on the drop. Millikan found that droplets had different charges, but each was a whole number multiple of a smaller charge, equal to negative 1.60 times 10 to the negative 19th coulombs. Millikan concluded that this was the fundamental unit of charge, the charge of an electron. From the charge of an electron and the charge-to-mass ratio of an electron determined by Thomson using a cathode ray tube, Millikan was able to calculate the mass of an electron. The mass of an electron, 9.10 times 10 to the negative 28th grams, is an exceedingly small mass.
Okay. This chamber, I'm pretty sure was evacuated, so that there would be no influence on the drops except for gravity and the charge on the plates. They didn't mention that. Okay, so now we've identified that an electron is part of the atom. The atom is not indestructible like atom. It can't be cut. Yes, it can. We don't do it in chemistry, right? Our atoms are whole and then we don't break them apart. But this is helping us understand what the atom is composed of, and eventually it will give us a structural basis for periodic table. And that'll become evident soon, I hope. Okay, Henri Becquerel, he was French, discovered radioactivity by observing the spontaneous emission of radiation by uranium. And he identified 3 forms of radiation that were coming from these radionuclides. One was gamma rays. He identified gamma ray as a high energy light particle, right? It's a photon of light. So this was coming from the decomposition of uranium. Beta particles are actually electrons coming from the nucleus of the atom. And of course, they didn't know about the nucleus then, but it was coming from the atom, very high speed. And then alpha particles were the most massive of all. The alpha particles were essentially a helium nucleus with no electrons attached. Right? So if we use He for helium, and it has no electrons, right? Helium should have 2 electrons. So with no electrons, it has 2+ charge. I'll explain that in just a few minutes. But it's very massive compared to the electrons, compared to other things. That's going to be important for the next researcher. Ernest Rutherford was an English chemist, physicist. And up to this point, the model of the atom was simply a bag with these electrons. We had identified the electrons, so they had electron particles in here. Right? And then the positive charge was just randomly distributed. So that's why it was given the plum pudding model name. It's like a plum pudding. The electrons are the plums scattered throughout the pudding. Okay. Rutherford didn't buy it. He proposed, and this is where imagination comes in. Rutherford proposed that the atom was not like that. The atom was actually a nucleus in the center with positively charged particles, and the electrons were out here somewhere. See, I better balance it if it's going to be neutral. Okay, so most of the mass of the atom is in the nucleus, and a lot of this empty space out here is occupied by the electrons. So he proposed an experiment that would test his hypothesis. He needed an atom, he needed a substance, something that he could place in the path of these helium nuclei coming off a radioactive element. And he used helium nuclei because they were so massive. They stood a better chance of passing through and doing something on the way through the material. So he chose gold because it was the technology for producing very, very thin films of gold was known at the time. He just beat it until it's thin. And it was just a few atoms thick. So he believed that with just a few atoms thick, that his helium alpha particles could make it through and be detected on the other side. Well, if his model were correct, some of them would go zipping straight through these electrons because they had virtually no mass, and this guy would outperform them and just push them out of the way. So most of them would go through and hit the detectors as like a bright dot on the other side. But some of them would get close to this nucleus, and positive charges repel one another. Plus they have mass. So they would go like this, or they might strike it, do that, or they might actually hit it and go backwards like that, if his theory is correct. So that's what his gold foil experiment is going to do. And I think I've got an illustration. It's an animation, but there's no voice attached to it. Yeah, they call it the alpha scattering experiment. This is a model of his experiment coming up. That's a lead box with the radionuclide in it. So it only comes out a hole on one side. And you've got screens there that collimate the beam, that is, make it straight. So you've got a hole in one and a hole in the other one, and only the ones that are going straight will go through both holes. That makes it a straight beam. So here we go with the alpha particles coming out of the lead box. Okay. Strike the first one. Second one, make it through. And now they're going into the experiment. Strike the gold foil. And most of them end up pretty much straight line. Some of them are deflected, just like I showed you. So this experiment proved that this model was garbage. And that's what happens to some theories and models. Right? If they can be that, oh, this is at the atomic level. There's the nucleus, that red ball. There you go. Okay. That was Rutherford's gold foil experiment. So now we know that the atom is composed of negatively charged electrons. It has a nucleus that has protons in the same magnitude of charge to balance the electrons, because we know that atoms are, unless we do something to them, they're neutral. So those charges have to balance. There was just one problem. And Rutherford recognized this. his protons that balance the electrons were not massive enough to account for all the mass of the atom, except for hydrogen. Every other atom had more mass than he could account for with these charged particles. So he proposed the neutron. In other words, a particle that was about the same size as the proton, so just a tiny bit more massive, and neutral. But he didn't have the time to deal with it. So he gave his research associate, James Chadwick, the job. And Chadwick discovered and proved the existence of the neutron. So Rutherford got a Nobel Prize for his nuclear atom, and Chadwick came along later and got his Nobel Prize for discovering the neutron. That's back when Nobel Prizes actually meant something. You know, when you give a president a Nobel Prize for peace and he just walked in the door and did nothing, and that kind of takes the shine off of the prize. Okay, so now the nucleus is small compared to the overall size of the atom, but it has most of the mass. That means if it's got most of the mass, but very small volume, it's very dense, very high density. You've heard of neutron stars? Heard of neutron stars? Right? They're like some stars at the end of their life, they collapse into nothing but neutrons. All the protons and electrons combine and make neutrons. And you got this thing, a teaspoon of it would like be the mass of the Empire State Building, something like that. So the density is very high for the atom. But since it's got a lot of space out here for the electrons, the overall density of the atom then goes down. Because you've got the same mass, but now you've expanded it to occupy this volume, and that decreases the density. Remember, density, mass divided by volume. So if we have the same mass and we expand the volume to some huge amount, the density goes down. Okay, this is a comparison of a nucleus of an atom, 10 to the minus 13 centimeters, and the overall size of the atom, roughly 10 to the minus 8 centimeters. So it's 5 orders of magnitude bigger than the nucleus. So when everybody know what I mean by orders of magnitude? Powers of 10. So if the difference between 10 to the minus 13 and 10 to the minus 8 is 10 to the 5th difference, I mean, multiple. Okay, so it's 5 orders of magnitude. It's huge. Now, Dalton proposed that everything, in his theory, everything was made of atoms. And that every atom was identical. Now, in one respect, it's true. All the atoms of an element are chemically identical, but they're not identical in terms of mass. We discovered that when we found isotopes. When we were finally able to separate atoms of the same element from one another, we found out that some of them were heavier than the others. Those are isotopes. The explanation for that is that the nucleus contains the same number of protons because the number of protons defines the element. If you have a different number of protons, you have a different element. But you can have different numbers of neutrons and have the same element. So that's an isotope. The variable number of neutrons determines different isotopes. And all naturally occurring elements are a mixture of isotopes. Some of them, most of them, in fact, have one isotope that dominates, like 90, some of them almost 100%, the same isotope. And then just have minor amounts of the others. There are a couple in there that have substantially weighted isotope numbers. Chlorine's one of them. And you can see that with the atomic mass, right? If chlorine is 17 protons and 17 and 18 neutrons, it would be approximately 35. But if it has 19 neutrons, it'll be 36. So 35 and 36, halfway in between that is 35 and a half. So chlorine is one of those where those two isotopes are almost equal in abundance. Okay. This is an example of isotope of sodium. 11 protons for both of them, but different neutrons. And the way they're writing the symbols, I think I've got do I have a slide on there coming up? Yeah, I got a slide on that one, so I'm not going to steal my own thunder. I'll show you why they write them that way. Here we go. Okay, when we have a symbol for an element, and I'm going to use X as just a placeholder. Any symbol, either a single capital letter or a capital and small letter for some elements.
Dr. Bly,
Yes.
I have a question. I thought that the reason that they found the neutrons was because it needed to be balanced out like the electrons to the proton. Am I wrong in understanding?
No, because the neutrons are neutral. So they don't have to balance anything. The reason that you have different numbers of neutrons in the isotopes is based upon the stabilizing effect that they have on the nucleus. Because when you start putting positive charges that close together in a nucleus, they want to push apart. And it's believed that the neutrons are there to help stabilize them. They exchange particles so that they hold on to one another. And that's why as you get larger and larger in masses for your elements, you have a larger abundance of neutrons in the nucleus, because the effect of that short range nuclear force is just that, it's short range. So you need lots of neutrons in there to compensate for the size of the nucleus. There's some rules of thumb that nuclear physicists go by to establish which ones are the most stable ones. But when you get past, let me see, paint myself into a corner here. When you get past bismuth, when you go to polonium and higher, polonium's 209. Yeah, these are smaller. When you get past polonium, you don't have any stable nuclei. They're all radioactive. You just can't get enough neutrons in there to stabilize them. Right. So it's not balanced with electrons, it's stabilizing the nucleus is the purpose of the neutrons. Now, on the smaller ones like helium, lithium, beryllium, boron, they're going to have roughly equal protons and neutrons because they're still very small. They only need a certain number to hold things together. But as you get bigger and bigger, you need more neutrons to cover that space. Okay, when we got a symbol, there are 4 positions around that symbol that are reserved for certain types of information. This one is going to be charge. If it's a neutral atom, you can write a 0 there, you just leave it blank. And it's implied that it's neutral. So you have the same number of protons, same number of electrons. If you have a number here, this is for the number of atoms that are in the molecule or in the compound as written. So when we write H2O, we know that there are 2 hydrogen atoms in that molecule with 1 oxygen. And we don't write the 1, right? If you have the symbol, you got to have at least 1, right? So it'd be redundant to write 1 in there. Over here, we have what's called the Z number or the atomic number. That's the number of protons. Okay, so in the previous example, it was sodium, wasn't it? Yeah, sodium. 11 is the atomic number. And in this chart, the red numbers are the number of protons, the atomic number. Up here is called the mass number. And these are always whole numbers here. Whole number, whole number. mass number is number of protons plus the number of neutrons. So when I write a little n with a 0 above it, that stands for neutron. When I write a little n with nothing, that stands for the number of particles. We're going to call those moles later. So if you know this number and that number, you can find out how many neutrons there are, right? Just subtract this one from that one and you get neutrons. Now, in chemistry, we don't have to write these when we're writing the compounds, when we're doing chemical reactions. This is for nuclear chemists. But it does tell us a lot about the isotope. It tells us whether you have a different isotope. If you have a symbol with the number of protons, and of course, if you have the symbol, you know the number of protons because it's right there. Or if you know the number of protons, you know which element it is. Right? They're joined at the hip. But if you have a different A, then you know that you've got two different isotopes. Oh, X has 23 protons. All right, so if we do this, and 28 neutrons. So it has 28 neutrons. What's the mass number? 51, right? 23 plus 28. This is not mysterious. It's not a mystery religion. It's just basic math. Okay. So the question is mass number. Okay, mass number is 51. Okay, mass number 51. How about the element? If we know it's got 23 protons, we just go to the periodic table. And they get larger and larger numbers as you go from top to bottom and left to right. So you just go across like that until you find 51 and wait a minute, 23, sorry, 23, which is right here. V stands for vanadium. So this would be the way we'd write it. Vanadium. I didn't have you memorize that one, did I? Oh yeah, I did. Okay. All right. So your review document should have several of those in there to give you practice. All right, how about bonding? Remember, Dalton's theory also said that the chemical reaction is simply a rearrangement of atoms. Well, when the atoms go in as compounds, they're bonded to one another in a certain fashion. Either we divide it into two types. They're bonded either covalently, I'll explain this in a minute, or ionically. These are the types of bonds. Ionic's easier to understand. You just have a negative ion and a positive ion, and they attract one another. It's purely electrostatic. Okay, the force here is electrostatic. Pure and simple. Electrostatic. Covalent is a sharing of electrons. So when two atoms approach each other, if they're going to bond, what do they see first? They don't see the nuclei first. They intermingle electrons, right? Because they're on the outside. So the electrons determine the type of bond. Now, the whole atom has to be, an integrated whole in order to determine what type of bond you're going to have. But the overlapping electrons and the sharing of electrons gives you a covalent bond rather than an ionic bond. And when you get a molecule, I'm stealing my own thunder again. When you get two atoms bound together covalently, you get a molecule. And that just means that when they're bound together, they behave as a single unit. They can be identified and purified to be that single unit. You can get hydrogens, two hydrogens bound together. right? And when you memorize those diatomic elements, hydrogen is one of them, H2, N2, O2, F2, CO2, Br2, I2. Those are all the diatomic elements. Memorize those as diatomics. The O2, or you can get molecules of multiples together, like, I don't know, say you're diabetic and your glucose is out of whack. You're going to have this molecule floating around in your blood in too large an amount. Okay. But these are all covalently bound atoms. They share electrons. For the ionic compounds, you're going to have a positive ion and a negative ion. And we write the simplest whole number ratio. Because when you get positives and negatives, they can be like this or they can be like this, but they'll always have the same ratio. So if you have one sodium ion and one chloride ion, they'll be like that. But if you spill salt on the table and look at it with a magnifying glass, then you'll see little cubes. And those cubes are arrangements of these sodium and chloride ions massively. So rather than write 10 to the 12th here and 10 to the 12th here, which would be ridiculous, we just write the simplest whole number ratio, which is 1 to 1. But we know that in ionic compounds, they're an array, a crystal array of ions. Okay. These ions have names. The positive ions are cations, and the negative ions are anions. Just memorize it. Now, but the reason that they form, remember, a neutral atom of sodium has no charge. A neutral atom of chlorine, now I'll lift the 2 off because we're only talking about 1 atom each, is like that. So they won't attract one another. But sodium has 11 protons and 11 electrons. And chlorine has 17 protons and 17 electrons when it's neutral. So how do they do that? Well, sodium just loves to give up an electron. So it'll transfer an electron over here. Right? If it's starts off with 11 positives, you can't change that number or you'll change the element. But you can change this number. If it loses one of those electrons, what's the net? The net is 1 positive charge. That's how you get ions, by adding or subtracting electrons. Now that we've added an electron over here, we have 18 electrons. So we have a net negative charge. Now you've got ions that attract. Okay.
So this is a video that addresses the question that students often have: what is the difference between a formula unit and a molecular formula? And that brings up a couple of questions itself. What are the structural differences between ionic and molecular compounds? And how do those differences affect their chemical formulas? So the chemical formula for a covalent compound is a molecular formula. And the chemical formula for an ionic compound is called a formula unit. So an example of a molecular formula, H2O, which is water, and for a formula unit, NaCl, the formula unit of common table salt. So what's the diff? And if we look at the structure visually, I think we can see very much what the difference is. So let's first look at sodium chloride. This will be our example ionic compound. NaCl does not exist as a single unit like a molecule, and this goes for all ionic compounds. So this would not be a valid way to represent sodium chloride. And like any ionic compound, in the solid state, sodium chloride exists as a crystal. So a very, 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 very tiny crystal would look like this with alternating sodium and chloride, and a little bit of a different view. The formula unit is NaCl, but if we look inside the crystal, the sodium and chloride ions are actually bonded to 6 oppositely charged neighbors. So if we shrink the ions, we can take a better look inside. And it's a little bit hard to see. So what we're going to do is take a look at a particular chloride ion, that one right there, and ask the question, how many sodium ions is the chloride ion close enough to bond with? Let's start with the head-on view first. And as we change the perspective, you can see there are exactly 6 sodium ions that the chloride ions is equidistant and can bond to. If we ask the same question of sodium, how many chloride ions can it bond to? Well, again, there are 6 chloride ions that it's equidistant to, and therefore the sodium ion also bonds to 6 chloride ions. So as you go throughout the crystal, you can see that is always the case. Because each sodium is bonded to more than one chloride ion and each chloride ion is bonded to more than one sodium ion, then you can think of all the ions in the whole crystal part of one single bonded unit. And the crystal below would be Na32Cl32. So you can imagine that would be very impractical given the enormous numbers of ions in a crystal large enough to see with our eyes. So only the ratio of ions is given, and that would be its empirical formula. But we call the empirical formula of an ionic compound the formula unit. And sodium chloride is the formula unit for the sodium chloride crystal, and it is the smallest whole number ratio of sodium and chloride ions in the crystal. So all formula units are the smallest whole number ratio of the ions in the crystal. That goes for all formula units. Here's another example, calcium fluoride. You've got 1 calcium for every 2 fluorides. The calcium is 2+, the fluoride is 1-. It has a slightly different crystal structure to account for, rather than the 1-to-1 ratio of sodium chloride, you have a 1-to-2 ratio of calcium fluoride. And if we shrink the atoms to take a better look and see how the calcium is connected to the fluorides, you can see that each calcium has 8 nearest fluoride neighbors, and so it is equally bonded to those 8 fluoride neighbors. And if we look at the fluorine, each fluoride has 4 closest calcium neighbors. And again, like sodium chloride, the whole crystal acts as one single bonded unit, and so we need to express the formula as the lowest whole number ratio, being CaF2. So what about molecules? How are they different? Let's take a look at water. We've got the space-filling model on the left, ball and stick model on the right. It's covalently bonded hydrogen and oxygen. And a collection of water molecules is just that, a collection of individual units of H2O that are covalently bonded single units of 2 hydrogens and 1 oxygen. They're not connected to each other except by weak forces. And so large amounts of H2O, any attraction between the water molecules due to weak forces, the molecules they still behave as individual units, not one large bonded unit as in an ionic crystal. Another view of water, here the hydrogens are white instead of yellow. And this I'm showing you to contrast more specifically with the sodium chloride or the calcium fluoride, because we showed the ionic crystals as solids, and here's water as a solid, ice of course. And here, like ionic compounds, molecular compounds also form crystals in the solid state, a very ordered structure that you can see here. If we take a closer look, however, we can see that each H2O remains as a single unit and is not covalently bonded to any other H2O. The attractions that hold them in place are, of course, the very, very strong dipole, the hydrogen bonding that occurs between the hydrogen and the oxygen. But that is much, much, much weaker than the covalent bond between the hydrogen and the oxygen, and the H2O therefore remains a single unit. So we look at these structural differences between molecules and ionic compounds by how we express them in their formulas. The molecule is represented by a molecular formula showing all the atoms present in the unit. The ionic compound is represented by the ratio of its ions. and that is called a formula unit. So here's the H2O molecule, and here versus the NaCl formula unit. Many sodiums and many chlorides, yet it's still just expressed as the lowest whole number ratio. It's 1 sodium to 1 chloride. In summary, in a molecule, the atoms given by the formula are all covalently bonded. In a collection of those molecules, molecules are attracted to each other by weak forces, but no covalent bonds occur between the molecules. The molecules exist as individual units of covalently bonded atoms. But in an ionic compound where the bond is the electrostatic attraction between oppositely charged ions, each ion is bonded to each of its oppositely charged neighbors. So for any ionic compound, all the ions in the whole crystal can be thought of as part of one single bonded unit. So the formula unit shows the lowest whole number ratio of the ions rather than representing very awkwardly all the ions in the crystal, which in most cases would be impossible to determine anyway. So that is the difference between a formula unit and a molecular formula.
So we're going to solve a problem here. By the way, I have a feeling that I'm going to run out of time. So my policy is, since there's nobody coming in this classroom after me, if I run out of time, I keep talking and I just keep recording. And if you have to go for a job or pick somebody up or whatever the reason, or you just don't want to be here, you know, you can go ahead and I'll keep recording and then post the video later and you can look at the parts you missed. Okay. I'll blame it on the school. They don't give me enough time. If we have an isotope that has a single positive charge, and we know that it has 54 electrons, okay, and we know it has 78 neutrons, okay, the question is, what's the mass number? Remember, the mass number is neutrons plus protons, but we're not given protons. Can we figure out what the proton number is? Yeah, that's the correct answer. We can. We have 54 electrons with 1 positive charge. That means we have 1 more proton than we do electrons, which means 55. So the mass number is 55 plus 78, which is, if I do my math right, 133. Okay, 33. Now, while we're at it, what element is this? 55. There it is. I haven't memorized it. Cesium. That's cesium. So we would write CS 133, 55 with a plus charge. Okay, concept check. Which of the following statements regarding Dalton's atomic theory is still believed to be true? Elements are made of tiny particles called atoms. Yep, that holds water. All atoms of a given element are identical. Nope, not with isotopes. A given compound always has the same relative numbers of types of atoms. Yes, that's still true. And the atoms are indestructible. No. So the only ones that are still true are Roman numeral 1 and 3. We can destroy atoms. We just don't destroy them in chemical reactions. We do in nuclear reactors or particle accelerators. We can do that. Or we can just let them naturally decay. Now, radioactive elements are used in chemistry. But usually that's in a chemical reaction where you want to know what the mechanism is. You want to know where atoms are moving. That way, if you can trace them, then you can better understand the reaction itself. But for typical chemists, bench chemists, we don't care. All right, periodic table is subdivided into two regions. And it's divided by this line here. If you do the extra credit, I'm going to ask you for a dark black line instead of the red. It starts between boron and aluminum and then stair steps like this. Everything over here is non-metal. And everything over here, metal. Most of the elements are considered metals. Now, what's the difference between a metal and a non-metal? They have various characteristics that describe them. Metals tend to lose electrons in reactions. Physical properties. If you polish a metal, it usually gets shiny. Many metals, most metals, in fact, are malleable. That is, pure metal can be shaped. In fact, pure iron, you can scratch it with your fingernail. They are good conductors of electricity. Okay. They're good conductors of heat. They're ductile, which is kind of like malleable. You can pull them through a small hole and stretch them into a wire. Whereas nonmetals, and all of them but one is solid at room temperature. Which one's not solid?
Yeah.
At body temperature, it's a liquid. At room temperature, it's still solid, just barely. No, mercury. Mercury is a liquid at room temperature. Whereas the nonmetals can be any I hate it when that happens. State. It can be any state, solid, liquid, or gas. We have some gases here, right? All the noble gases. That's a gas. That's a gas. That's a liquid. That's a solid. And the solids are brittle. Right? They're not malleable. Okay, and the solids are also dull. They don't shine like metals do. Of course, now very finely divided metal is black. Okay, we can also subdivide them into groups. We used to call them families. They're the columns. Some of the columns have names. Far left over there, the alkali metals, not including hydrogen. We put hydrogen over there for balance. That's it. Hydrogen is it's an animal, different animal unto itself. But lithium, sodium, potassium, rubidium, cesium, francium, those are all alkali metals. Next door to them is beryllium, magnesium, calcium, strontium, barium. Those are alkaline earths. Then we have this group in here between these two. Those are transition metals. Let's see. Then if we start from this side, we have the noble gases, or the inert gases. Then we have the halogens. Then we have the chalcogens, which is kind of holdover from olden times. Based upon the formation of compounds with oxygen, they were called calx, CHALX. So these are the chalcogens. These are the nicogens, which starts with a P, PNICT, nicogens, for nitrogen. And then these don't have names, boron group, carbon group. We also can say that these two columns and these 6 columns together are called representative elements. I'm not sure where they got that name, but I'll explain it to you later. We get certain periodic trends in those 2 and these 6 that kind of get wonky in here. So if we use only those 2 and these 6, our periodic trends tend to behave better. Now, those are the columns. The periods are the rows. And has anybody here had physics? You know what periodic motion is? Think of a pendulum on a clock. It's moving, right? But it doesn't go anywhere. It goes through a cycle. It goes from here down to here and then back to here. So in one period, it goes through a swing. And for chemical reasons, we get a period going across here, and then rather than make another column here, we find that rubidium is very much like potassium. So we start a new row. It goes through a period, cycles back. Now, before the semester's over, you're going to know why that happens. All right. So there's another representation with some of the names, not all the names. If you do that extra credit, then you'll get all the names that I gave you up there. And hopefully imprint them on your brains and get credit for them too. Okay. Now, some of these elements, when they acquire a charge, prefer one charge over other. The alkaline metals, that first column, they prefer +1 charge when they become charged. The alkaline earths, the second column over, they prefer a +2 charge. Not boron, but aluminum. Aluminum, gallium, indium. When they become charged, they prefer a +3 charge. So 1, 2, 3. Then if we work from the other side, the noble gases don't charge. You really have to force them to get a charge out of them. So for our purposes, they're neutral and they stay that way. They don't react with anybody. The halogens prefer a -1 charge. The chalcogens, when they're charged, prefer 2 charge. And the nicogens prefer a -3 charge. Okay. The carbon group in the middle, at least up here, carbon and silicon, they can go either way. They can be plus or minus charge. Let's see. Okay. And that's when they create ionic compounds. They typically create ionic compounds only when metal and non-metal react. If you get two non-metals reacting, they tend to form covalent bonds, sharing electrons. But these guys want to give up electrons, these want to accept electrons. That's how you get the cation and anion interaction. In your periodic table, you may notice, let's see if it's in this one. Yeah, in the upper right-hand corner, you may see multiple charges. Those are not all charges. You can be pretty sure that the first one at the top is a charge, but the rest of them might be oxidation states, which is kind of a bookkeeping scheme, not really charges. Or they may be assigned also to, let's see, formal charges, which is another way of bookkeeping. All right, we haven't got there yet, so don't let that bother you. I just don't want you to think that those numbers are all charges. The values I gave you right now are the, and the transition metals. The thing about the transition metals and some of these right here is that they can acquire different charges, multiple charges, depending on what they're reacting with. And we're going to cover that in this naming convention. Okay, I'm out of time. So if you have to go, you can go. But if you do, be sure and watch this video because this nomenclature is extremely important. If you don't know how to write compounds and name them, go backwards and forwards, either way. Write the compound from the name or name the compound from the formula, then you might as well drop the course because you're just not going to survive. All right, so we have a pretty straightforward method for naming compounds, and the rules are devised by subcommittees of this international group. the International Union of Pure and Applied Chemists has jurisdiction over naming compounds. And they can get pretty ridiculous. You know, these huge molecules, they can have names that are as long as this room. But we're going to start simple with binary compounds. Binary compounds are just compounds of two elements. Okay. All right, and those compounds can either be formed of metals and nonmetals or two nonmetals. And I subdivide them into three types. Okay. Type 1 compound. These are always metal, nonmetal. Okay. And metal is a fixed charge. And what I mean by that is it's one of those metals that can only have one charge and no other. It never assumes a different charge in a chemical reaction. And those are the ones that I gave you. The first one column is +1s, +2s, +3s, -1, -2, -3. Well, the metal, let's stick with the metals. Sorry. The metals. So it'd be +1, +2, +3, and let's see. I think I don't want to misspeak. Okay. And metals with fixed charge are silver is +1 always, cadmium is +2, and zinc is +2. So those are fixed charges. Those columns, these guys, and these three are always fixed charges. So they would fit into the metals of a type 1 compound. We always name them with the metal first. So let's take an example. Say sodium combined with chlorine, like I drew earlier. We changed the second one, the anion, we changed the ending to IDE. So it's sodium chloride. Now we can write the compound from that if we know the symbols. Sodium and chlorine. Now, what charges do they assume? Well, sodium is always +1. That's why it's a type 1 compound. And then chlorine is -1. So we have balanced the charges. We only need one sodium and one chlorine to satisfy that name. Okay. The naming conventions are designed to do two things. To be one, unambiguous. In other words, when you write that name, this is the only possible formula that will fit. Or when you write that formula, this is the only way to name it. Right? And the second condition is non-redundant. That is, you don't have to repeat yourself. So if we said, if we wanted to put the charges in there and we said like this, sodium has a +1 charge and then chlorine, that would be redundant because sodium can only have a +1 charge. No other possibility. Right? That's not redundant. Okay, that's the type 1 compounds. And there are some examples. Potassium, of course, is a +1 charge, chlorine again, so it's only KCl. Magnesium, however, is an alkaline earth. It has a +2 charge. And since bromine is a halogen with 1 minus charge, the only way to balance the charges is 1 magnesium and 2 bromines. So magnesium bromide is the name for that compound. Why? Because magnesium has a fixed charge. Calcium oxide. Calcium is a +2 charge. It's in the alkaline earths. Oxygen's a chalcogen, so it has a -2 charge. So you just need one of each. And we only have to call it calcium oxide. We don't have to say anything else. We know without any possible error, unambiguous, that CaO is calcium oxide. Okay, type 2. Type 2 compounds are also metal, nonmetal. But the charge for the metal is variable. Now, that doesn't mean that the charge varies once the compound is formed. Once the compound is formed, that's the charge, it's fixed, it doesn't change. But on the way in, to make the compound, it could be one of 2 or 3 or 4 different charges. If that's the case, then we have to say what the charge is in the name. For example, if we had this one. Okay. Iron oxide. That's not the complete name. It names this part and that part, but we don't know what the charge here is unless we do the calculation, right? Oxygen is always 2 minus, right? So 3 times 2 minus would be 6 minus, correct? For the oxygens. To balance that, we need 6 pluses, right? Because it's a neutral compound. 6 pluses for the irons, but there are 2 of them. So we split them evenly between the 2. This is a 3 plus. Okay. So now we know the charge on iron, and we say iron, give it the charge, Roman numeral 3, oxide. Okay. Most of the variable charge metals are going to be transition metals, and then over in this region over here underneath. And you can find those in the periodic table. Okay, so there's some more examples. I'm going to come back to polyatomic ions in just a minute. I gave you a copy of the polyatomic ion list, and we'll come back to that. Let's get type 3 done, and then we'll come back. Type 3s are a non-metal, non-metal. Okay. Because they're non-metal with non-metal, there are no charges. Right. It's not, they can't completely transfer electrons from one to the other because they don't want to give them up, right? Non-metals don't want to give up electrons, but they will share them. And to make things simpler, we use part of the naming convention from these two to help us over here. In other words, if we have something like carbon and oxygen, we have that formula. Then we don't have a charge, right? Because they're both nonmetals. So we say carbon, and then we have the oxide, but because there are no charges, we can't tell how many, of what ratio they are. So we say carbon, and we just say how many. We use the Greek prefixes for 1, 2, 3, 4, 5, up through 10. That should be, maybe it's on the next slide. Yeah, it's on the next slide. If we did this one, let's see. Let's do it this way. This is a different compound. Same 2 elements. We want to write the formula. Carbon, oxygen, but there's only one of them. CO, that's it. Okay. This is the product of combustion, that combustion of, say, methane in air. This is the incomplete combustion. Comes out of your tailpipe, right? That's the one that kills. Does anybody know how carbon monoxide kills?
Doesn't it bind with the red blood cells and it doesn't let them carry oxygen?
Yes, right. It excludes oxygen from the hemoglobin by binding, not irreversibly, but very strongly. Carbon monoxide will bind with the iron in hemoglobin, and that way it can't carry oxygen. So you suffocate at the molecular level. Now, if you catch it soon enough, you can put your victim in a hyperbaric chamber, flood the system with oxygen, and over time, the carbon monoxide will be released. It's a slow process. Okay. Let's see, we've got some other examples in here. Oh, we got the prefixes. So one thing you'll notice is with only one carbon, we don't say mono for this position. We don't say monocarbon. We only say di if there are two of them or maybe more. But the second one always gets the mono. I think it just flows better. And we don't say monooxide. We just drop one of the O's. Chemists believe in aesthetics sometimes. So mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. Those 10, if you know those, you'll be okay for the rest of the course. There are a lot more, of course, especially for organic chemists. They go hog wild. Okay, how about this one, SF6, sulfur, fluoride, and we have 6 fluorides, so sulfur hexafluoride. N2O4, we have 2 nitrogens and 4 oxygens, so dinitrogen tetroxide. All right, so let's go back to the polyatomics. Okay, polyatomic ions. Let's see, did I miss a slide there? Yeah, polyatomics. Polyatomics are covalently bound groups of nonmetals that carry a charge for the whole group. So they behave as ions. For instance, nitrate. That negative charge is not assigned to just one of those oxygens. That's for the whole group. That negative charge is spread over the whole group. Okay? Or sulfate. That 2- charge is spread over the whole group. But for our purposes, it behaves like a simple anion. So we can use these anions in any one of these. We can put nitrate over here. If we have another, say, I don't know, what would go good with nitrate that's not a polyatomic? It'd have to be a metal, right? Because we need a positive charge. So I guess yeah, we're talking about here for the polyatomics, for the 1s and 2s. Okay. So you gotta have a metal with these ions. It could be this one or this one, depending on the metal. Is the metal a fixed charge or a variable charge? And it could go either way. So if we had this one, how many of these would we need? Well, 2 times 3 is 6 plus, so we need 6 minuses. Right? And that's the way you make multiple polyatomics is with parentheses. Because the charge is spread over the entire unit, you cannot mess with the subscripts. They're fixed. And the charges are fixed also. And that's why I gave you that list. That list is actually the same list on the left as the right. On the left, you're sorted by name. So if you know the name, you can find the formula by looking down the left-hand side alphabetically. If you know the formula, then alphabetically with the formula, you can look down the right and find the name. Okay, so that way you don't have to memorize them. Although there are some patterns in there that help you memorize them if you want to. Let's see. And we did those. Okay. Now, what do you do if you're confronted with, on a test, say, with a compound, and I want you to name it? You look at how it's constructed. Is it a metal and a non-metal, or a metal and a polyatomic ion? All the polyatomic ions in there are negative, except for one. This is the only positive one in there. Ammonium. And their names are fixed. You don't change their names at all when you put them into a compound. So rather than, you wouldn't say IDE on this sulfate, right? So sulfide would be this. 2 minus. Sulfate is that. So the names of the polyatomics are fixed. Excuse me. So when you're confronted with a compound and you have to name it, you look for the metal. Is there a metal in there? Or is there this right here in that metal place? If this is in there, like this one, ammonium nitrate, you know, the IED maker's favorite chemical. Ammonium nitrate, then this is fixed, so it's a type 1. Right? It's not a metal, but it fits the bill. It's a fixed charge. If you went over to here, then we did one like that. That would be iron 3 nitrate. That. So you look for the metal. If it's got a metal in it, it's either this one or that. If they're 2 non-metals, it's got to be this one. Then if it's got a metal in it, you have to decide. You branch and you say, is it a fixed charge metal or a variable charge metal? And then you use one of these. That's those are the steps that you follow to get to the answer. If you like flow charts, there's another one. Now, I think the last naming convention is for acids. Well, the next to the last is acids. So, let's define an acid in chemical terms. For our purposes, binary chemicals, acids start with hydrogen. That's the first element in their name. So if we did this, then if we named it by our convention, this would be a type 1 compound. This would be hydrogen chloride, right? And that's what it is if it's a gas, hydrogen chloride gas. But if you bubble it through water, if you dissolve it in water, then it becomes aqueous, AQ. It becomes hydrochloric acid. Now notice what we've done there. You have to have the at least one of these. Sometimes you have 2 or 3 in the first elements in the compound. And sometimes there are hydrogens in the rest of the molecule too. But those hydrogens don't contribute to the acidity. They are bound. But these can be separated from the molecule, and that's what gives it its acid characteristic. So with say acetic acid, right? You're making a salad with vinegar and oil, you're using acetic acid and vinegar. There you go. That's the hydrogen that makes it sour. These hydrogens are stuck. They don't move. Okay. So this would be hydrogen acetate. That's a polyatomic ion. But if you put it in water, then the 8 becomes ic. And this is acetic acid. Now notice the difference here. I started this one with hydro, but I didn't start that one with hydro. That's the naming convention. If the molecule has oxygen in it, you don't start with hydro. It's only when the oxygen is absent that you start with hydro. And then you say chloride becomes ic, or ATE becomes ic. These naming conventions, what we're trying to do is standardize the naming convention based upon what we were grandfathered by alchemists, because they'd already named these things, and we needed to standardize them so that we could proceed to other compounds logically. All right. So hydrochloric acid is this one. H2S, hydrosulfuric acid. Sulfide becomes ic, and we say sulfuric just because it sounds better rather than sulfic. Cyanide is a polyatomic ion, Cn minus, cyanide ion. So it's hydrocyanic acid. If they're dissolved in water, okay, that makes them acids. If it's HCN gas, right, which would be deadly, it's hydrogen cyanide. Okay, here's some polyatomics. Nitrate becomes ic, HNO3, nitric acid, and just assume that these are dissolved in water. SO4, sulfate becomes ic, sulfuric acid, and we did acetic acid already. Actually, vinegar is 5% by weight. Acetic acid in water. Okay, NO2 is not nitrate, it's nitrite, and ites become us. So whereas HNO3 is nitric acid, HNO2 is another polyatomic ion with the same charge, -1, -1. This is nitrous acid. Okay. And SO3 is sulfite rather than sulfate. SO4 is sulfate. SO3, 2- is sulfite. So that's sulfurous acid. Okay. Let's see. And there's a chart, flow chart for acids. All right. I will give you one example. If you're planning on heading into chemistry, or if you're just interested, these polyatomic ions, some of them have a pattern to them. And this one, right, that is the chlorate polyatomic ion. If we take away one oxygen, we get chlorite. And if we take away another oxygen, we get hypochlorite. Right, hypo underneath, like hypodermic, under the skin, underneath chloride. And if we add one more oxygen, we get perchlorate. Okay, so you got a sequence of 4 here just by starting from there and working your way down and up. And you can do this with any of the halogens. Put bromine in there, it's perbromate, bromate, bromite, hypobromite. You can use iodine, that's periodate, so forth. So you can get 12 just like that, 12 of these names, just like that. Now, if we make acids out of them, notice that protons are +1 charge. So you only need one proton for each of these. If we add a proton for each one, and they've all got oxygen, so we don't start it with hydro, then this would be perchloric acid. This would be chloric acid. This would be chlorous acid. And this would be hypochlorous acid. Okay. Let's see. I know you've seen this one before. Well, you don't read labels, do you? Okay. Read the labels on a bottle of bleach. There you go. Sodium hypochlorite is bleach. And it's various compositions. Some of them are, used to be 5% was all you could get. Now you can get 6.5% regularly. Okay. So I think that's close. Which of the following compounds is named incorrectly? In this case, you see, is it a type 1, type 2, or type 3? And then you see if that matches the name. Potassium is a type, would make it a type 1. Potassium nitrate, that's correct. Titanium is in the transition metals, and it's not one of these. So we have to figure its charge. Oxide is 2-, so 2 times 2- is 4- total, right? So that one titanium has to be 4+. And it's not named correctly. That needs to be a 4 Roman numeral, not a 2. OH, hydroxide, that's a -1 charge on a polyatomic ion, OH. So it's -1 times 4, and that means 10, SN has to be +4, and it is in the name. So we're good. PBr5, those are both nonmetals. So phosphorus pentabromide is correct. Chromate is a polyatomic ion with a 2- charge, and calcium has a fixed 2+ charge. So one of each is all you need. That's good. Calcium chromate is correct. The only one that's wrong is that titanium compound. Okay. Oh, last one, waters of hydration. Reason I stuck this one on here is because we have a lab. I think it's the 3rd lab where we're actually going to determine the waters of hydration for a compound. What do we mean by waters of hydration? When metal compounds are either precipitated from or left after water is removed from them, dissolved in water, they're left behind. Typically what happens is if you heat them to dry them, say at 105 degrees Celsius, drive off the water, very often there's some water left behind in that crystal structure. Those are waters of hydration. They exist as water molecules in the crystal matrix. Okay. So when that's the case, and our example here is zinc sulfate. Now you can get anhydrous zinc sulfate. That's possible. They just heat it to about 150 degrees Celsius for a couple hours. You'll drive off all those waters of hydration. But it typically, if you only dry it at 105 degrees, it typically has 7 waters in molar ratio of 7 water molecules for every 1 zinc sulfate unit. That's the ratio. The one we're going to do is copper sulfate, and it has 5. Now, just because you know that doesn't mean you don't have to do the experiment. You can do the experiment and prove it, okay? But the way we name them, we name these just like we did before, right? Copper could be copper 1 or copper 2. In this case, it's copper 2. So we would say copper, 2+ charge, sulfate. And then we say hydrate, and how many of them are it? So in this case, it'd be penta. Pentahydrate. That's how you name a compound waters of hydration. Okay, I think that's the last slide. Yep.